What if a mysterious force that existed only in the earliest moments of the universe could solve two of the most confusing puzzles in cosmology? That's precisely what scientists from MIT are exploring with the concept of early dark energy. This concept could not only resolve the Hubble tension, a conflict over the universe's expansion rate, but also explain the unexpected discovery of numerous bright galaxies in the early universe by the James Webb Space Telescope. In this video, we will delve into the new study of how early dark energy can resolve the Hubble tension and other cosmic puzzles. So without further ado, let's get started. The Hubble tension and the role of early dark energy. Let's start with the Hubble tension, one of the biggest mysteries in modern cosmology. The Hubble tension refers to a significant discrepancy in measurements of the universe's expansion rate, known as the Hubble constant. On one hand, observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, by experiments like the Planck satellite suggest one value for the Hubble constant. On the other hand, measurements based on the brightness and distance of type Ia supernovae in relatively nearby galaxies indicate a higher rate of expansion. The difference between these values isn't just a minor inconsistency. It suggests that something fundamental about our understanding of the universe's expansion might be missing. You can watch our full video on this difference. You will find the link in the description. Now here's where early dark energy comes into play. Early dark energy, EDE, is a hypothetical form of energy that may have existed only briefly in the universe's infancy. According to recent research by MIT scientists, early dark energy could have provided a fleeting but powerful repulsive force, much like an anti-gravity effect, just after the Big Bang. This force would have accelerated the expansion of the universe for a short period, impacting the measurements of the Hubble constant derived from the CMB. The evidence for early dark energy comes from its potential to resolve the Hubble tension. By incorporating EDE into cosmological models, researchers found that it could increase the inferred expansion rate of the universe at early times, aligning it more closely with the higher expansion rates observed in the local universe. In simpler terms, early dark energy might be the missing ingredient that makes the different measurements of the universe's expansion rate agree with each other. So why is this so important? If early dark energy is confirmed, it would mean that our understanding of the universe's history and structure needs to be updated. It suggests that the universe underwent a phase of rapid expansion not just during inflation, an already accepted theory, but also during this brief period of EDE influence. This would challenge the current lambda cold dark matter model, which is the standard model of cosmology, opening up new avenues of research to better understand the universe's first moments. If early dark energy truly existed, it could help us understand other phenomena tied to the early universe, such as the formation of the first structures and the evolution of cosmic inflation. The mystery of bright, early galaxies and EDE's explanation. The James Webb Space Telescope has revealed a surprising abundance of bright, massive galaxies that existed when the universe was only about 500 million years old, just 3% of its current age. These galaxies, comparable in size and brightness to the Milky Way, challenge our understanding of how galaxies form, which typically involves a slow process over billions of years as the gas cools and condenses into dark matter halos. According to a recent MIT study, early dark energy might be the key to explaining these unexpected observations. In the absence of early dark energy, dark matter halos, which act as the invisible skeleton around which galaxies form, would develop more gradually, resulting in fewer large galaxies in the early universe. However, if early dark energy existed, it could have caused larger density fluctuations, speeding up the formation of these halos. This would result in a more dynamic, rapidly expanding early universe, allowing galaxies to form faster and more abundantly, aligning theoretical models with Webb's findings. This connection between early dark energy and galaxy formation is more than just a coincidence. If early dark energy did cause a brief but significant acceleration in the universe's expansion, it would mean that galaxies formed in a different cosmic environment than we previously thought. The increase in early dark matter halo formation would create fertile grounds for the early and rapid assembly of bright galaxies, helping to explain why Webb sees so many of them. This suggests that our models of galaxy formation need revision, and that early dark energy might play a crucial role in understanding not just when galaxies form but how they grow and evolve over time. Moreover, this hypothesis ties directly into the broader search for answers about dark energy and dark matter, two of the most mysterious components of our universe. Understanding early dark energy could provide clues to these larger cosmic questions and help us piece together a more comprehensive picture of our universe's history. Broader implications of early dark energy for cosmology. Beyond solving the Hubble tension and the mystery of early galaxies, early dark energy could have even broader implications for cosmology and other fields of physics. To fully understand its impact, we need to look at what future missions and interdisciplinary research could tell us about this mysterious force. Upcoming missions like the Simons Observatory and CMB-S4 are designed to measure the CMB with unprecedented precision. Similarly, large-scale surveys like Euclid and the Nancy Grace Roman Space Telescope aim to map the distribution of galaxies and dark matter throughout the universe. These missions could provide crucial evidence for or against early dark energy by looking for specific signatures. Scientists would search for subtle variations in the cosmic microwave background or galaxy distributions that could indicate a brief phase of accelerated expansion in the universe's early history. Moreover, any unusual gravitational lensing effects, where light from distant galaxies is bent by massive objects, could reveal discrepancies pointing to early dark energy. What makes these missions exciting is their potential to either confirm or rule out early dark energy as a real phenomenon. If they find evidence consistent with early dark energy models, it would solidify this idea as a key component of our understanding of the universe. Conversely, if they don't, it would push scientists to look for alternative explanations, further advancing our knowledge of cosmic evolution. Now let's consider the cross-disciplinary impact and theoretical implications of early dark energy. This concept doesn't just affect cosmology. It could have profound implications for particle physics and theoretical frameworks like string theory and quantum gravity. If early dark energy is confirmed, physicists might need to look for new particles or forces that could produce such an effect. This could lead to the discovery of axion-like particles or other unknown components that extend the standard model of particle physics. Furthermore, theories like string theory, which seeks to explain all fundamental forces of nature in a single framework, could provide the mathematical structure needed to understand early dark energy's behavior. Lastly, let's touch on the impact on cosmological parameters and structure formation. If early dark energy affects more than just the Hubble constant, it could alter our understanding of key cosmological parameters such as the amplitude of density fluctuations and the matter-power spectrum. These changes could lead to a more nuanced view of how galaxies, clusters, and cosmic structures form and evolve. It could also provide a new context for interpreting the cosmic microwave background and other critical observations in cosmology. Outro. Thank you for joining us on this deep dive into the mysteries of early dark energy and its potential to reshape our understanding of the universe. If you found this exploration of cosmic puzzles as fascinating as we did, don't forget to give us a thumbs up and subscribe for more exciting content on the latest discoveries in space and science. We'd love to hear your thoughts on this topic, so feel free to share your comments below. Until next time, keep looking up and stay curious.